In the last lesson, we wrote current density for a point source and a dipole. Now, we finally do something useful with that source model. We place the cleanest possible source, an ideal point source, into the vector potential integral and watch the expression simplify. This is the first full source-to-field example in the series. To keep the geometry clean, put the point source at the origin. The observer sits at position vector r. Because the source is concentrated at one location, the source point and the origin become the same place in this example. That one choice removes a lot of notation immediately. The delta function now does the real work. Inside the integral, it says, ignore the rest of space and keep only the contribution from the chosen source location. So instead of integrating over a spread-out source region, we sample one point. That is why the point source example is the cleanest first radiation calculation. Once the source collapses to one point at the origin, the source to observer distance big R becomes simply R. The vector potential therefore takes the familiar form of a constant times e to the minus j k r divided by r. This is the first big payoff of the lesson. A compact source description has turned into a compact radiation expression. If the point source is not at the origin, the story is still the same. The only thing that changes is the distance term. Instead of r, we keep the full source-to-observer separation magnitude, so the point source result is not tied to the origin. The origin case is only the cleanest first version. Read the result in two parts. The 1 over r factor says the amplitude weakens with distance because the wave spreads over larger spherical surfaces. The exponential phase term says the disturbance is propagating outward and accumulating phase as distance increases. One factor tells the spreading story. The other tells the travel story. Now compare two observers. If one observer is at distance r and another is at distance 2r, the second observer does not receive the same field. Its amplitude is cut in half by the 1 over r factor, and its phase is delayed by an extra kr in the exponential term. So even this toy example already shows the two key ideas, decay and phase progression. That is why the point source example matters. It is not the final antenna we care about, but it is the cleanest source-to-field example we can solve first. The delta localizes the source. The integral collapses. At the origin, big R becomes R. And the result reveals spherical spreading and propagation phase in one expression.